With that, I want to say welcome to Sean. Sean is a friend of mine. We met at KCDC back, I believe, in 2021, and again this year, and I think maybe even a couple other conferences as well. It's really a pleasure to have Sean on Cincinnati Software Craftsmanship this month. Please give Sean a big CSC welcome and a little applause in the chat, if you don't mind. Welcome, Sean.
Thank you, Michael. I really appreciate it. This is fun to speak to your group. I really appreciate the opportunity.
Thank you. Thank you for coming on. With that, I'll let you take it away. And yep, thank you very much, and have a great time.
Awesome. So yeah, if you guys are on Twitch, I am used to stream on Twitch. I haven't done so in quite a while, but so if you see me in the chat as Code with Sean, that is myself. One of these days I might get back to streaming. Try to do that on occasion. It's just been a while, but anyway, when I do stream, it's definitely things like tonight's topic, where I'll work on a slide deck, building up other talks, maybe for a conference or things like that. And so what we're going to talk about tonight is network fundamentals for developers, mainly understanding how computers talk. And already had some feedback once on this title, and I try to make it as much as possible evident. So I'm talking about TCP/IP related networking, not how people talk. So, all right, let's get started. Now, a lot of you guys have obviously devices at your house. And from a laptop to a server, maybe you've got, your home router, you've got all kinds of, maybe you got some cables, probably more Wi-Fi these days. Chances are you've got multiple devices, multiple laptops, maybe multiple desktops, gaming systems, things like that. And the challenge, as we're seeing it these days, is that the types of devices and the number of devices keep growing, such as you'll get more smart TVs and even game systems like Xbox and PlayStation. And even things that, in my personal opinion, do not need to be on the internet, but some are. Things like your washing machine and your refrigerator. Me personally, I just assume that nobody in the world knows how much dirty laundry I process in a week. It's none of their business. But for some reason, these kind of devices are on our networks. So how do they talk? How do they get to the internet? Now, it's first off kind of basic to understand that, well, there's some sort of a router that we call it a router because that's kind of what we've been told. And you go to Walmart, you go to Best Buy, whatever, and I hope you don't actually. Those general are terrible. But I apologize if I keep cutting out. I don't know what is actually causing that, and I am on a hardwired line to my own router directly, so I'm bypassing anything Wi-Fi. But if Michael, if it does get to be a problem, let me know, and we can take a small break, and I'll see if I can change some configuration. So with these devices, they got to connect to a router, and the router has multiple functions. And one of which is being a switch, and the other one is being a router that routes the traffic, that network traffic, out to the internet itself. So we're going to look at that router and specifically how it has two different sides, that wide area network called the WAN, the other side called the LAN, the local area network. When you have devices that need to talk to each other on your home network, that is on the LAN side. That's that local area network side. And that router knows whether or not it's destined for something that's already internal to itself, that home network, or if it needs to go outbound and get out to maybe the internet. Maybe it's a more of a parent router, depending on where you're at. If it's your home devices, of course, you go straight to the internet. But if you're in a business, or even how traffic actually gets across the internet, Like for me, my traffic, I'm in Tulsa, Oklahoma, traffic's going to Tulsa, and then it's probably going to Kansas City, hitting major backbones up there with MCI. And so there's multiple routers involved in those hops. But for what we're going to talk about is not nearly that detailed. We're going to stay right here where we're trying to look at if we have a home device and we're trying to reach a website that's available on the website, in the internet. What is being sent is what's called packets, packets of information. Now imagine you have a very long conversation that needs to happen. You've got a lot of data that needs to be transferred. And the way that that's done is it's kind of blocked up so that it's in what these called packets, and these packets can only get so big. Think of a packet as kind of like a personal train car, where is it's only so big, and you can only put so many people in there. But with a long series of packets, then you can get that conversation across, or that that basically that amount of data from a source to a destination. Now, how does it get there though? And first thing that happens is that, for example, you open a browser, you go to google.com, and well, the name is actually not the real address. And the name gets translated to an actual address, and that's that IP address that we're talking about. And this translation is done with DNS, that domain name service. And I jokingly put, if you're already a JavaScript programmer, you probably catch more of the triple equals. If you're running things like Windows, you can run the command ipconfig /display DNS, and you can see some of that DNS information there. You can also flush the DNS information, which this has to happen on occasion. Sometimes that information gets some misinformation in there. I'm not really sure how that can happen, but it does from various times. I've even fought with it once before when I was trying to clean off a virus off of a computer, and it was trying to control the DNS information. So sometimes you will have to clean that DNS information. So think of a DNS as like a phone book. It has name and it has an IP address for your destination. It's going to help you with that translation going there. But there's a little bit more to that. We're going to explore that for a little bit. So the first analogy that I have is, imagine on your phone, you're going to pull up a friend. So for me and Michael, he may know Chad Green. He runs the user group, multiple user groups over in Louisville, Kentucky. And my first presentation of this talk was actually to his group, so it was easy to put his name in there. So when I don't know Chad's number, I know I have Chad's number, I just don't know what it is, because my phone has it, and that's a little phone book for me. So I have a name, such as that domain name, but I need to get it translated to an actual address, such as a phone number. And now, obviously, that's not Chad's real number, but if you do call it, he'll probably charge you by the minute for correct answers. So now, with DNS, there's multiple types of entries in there that for that domain to IP address translation. What we're talking about here is the A records. Those are when you translate a name to an IP address. Other ones are like a C name, which is for aliases. You'll know those specifically for if you've done www.google.com. The triple W is an alias to the base domain of google.com. You don't have to do it that way. You can do subdomaining elsewhere for other ways, but C names are for when you do aliases like that. MX records are for mail exchange. So when mail servers have to send that email addresses from one mail server to another, it does that with those MX records. They're not the same type of DNS records. Similar, but different. So there's a tool called NSLOOKUP that we can use to look at various information. And if we were to set the type equal to NS for the name service, then we can see those examples I'm talking about where we take a name to an IP address. If we set the name to MX, then We've got the mail exchange. If we do CNAME, then we can look at the aliases. And if we do quad A, then we can see the information about the IP version 6, which has been out for quite a while. And we're going to touch on that a little bit later. But right now, we're going to stick with for the discussion of the IP version 4. So let's look at another example. I pull up on my laptop, and we're going to pull up a friend of mine's website where you can view multiple user group recordings and other conferences for the last several years. And a friend of mine does this for free. He does this for several people and storing those videos for anybody. But if I go to usergroup.tv and I do an NS lookup on that address, I actually get 4 addresses in return. And you notice that in the middle, we got 108, 109, 110, 111 as being the differences on there. So how his website is being hosted, they are providing 4 different public IP addresses for high availability. But the DNS resolves to any one of those. Also, google.com does the same thing. You might hit different IP addresses, and it may also depend on where you are in the US, which actual address you may receive. So that's DNS in a nutshell. And yeah, I highly suggest usergroup.tv. I run a user group. So many of my videos are up there. And I'm more so plugging my friend's site than my user group because he's got conferences recordings for the last several years, and there's some fantastic stuff on there. So, all right. So now we understand about name translation. Let's talk about a little bit of routing. Because when I mentioned that we need to go from our laptop and we're going to open a browser, we're going to type in, google.com, and we see a site. Well, that information gets routed, and we're going to journey on through another analogy, so follow along with me. If I'm going to send a piece of mail to Chad Green, and I need to find his address, right? Remember, I've got his address in a phone book, and so now I got Chad Green at 123 NE Street, Louisville, Kentucky 40245. And yes, obviously not his real address. In fact, he's not even in that zip code. I double checked. With routing of the information that's from a source to a destination, let's take the perspective of a home device, such as the laptop I'm in right now. The information hits the router and it dissects the destination. So it's quickly determining if this information, this packet of data needs to go out or stay into the local network, that LAN. So what it does is we look at this information a little differently. What it's going to do is look at that zip code. Now, obviously, routers don't use zip codes. What it's doing is it's looking at the actual address of the destination and see if that's something within itself or if it needs to go out and cross that boundary. But with this example, this analogy, we can see that it's first looking at the zip code. If a piece of mail is going to go to your neighbor down the street, and you put that in the mailbox, it's going to go to the post office. They're going to see it's on the same zip code, so it doesn't go to another post office anywhere else. That one post office handles that, and they put that the destination, so it goes right to that house down the street. If it needs to go outside of that zip code, well, then it registers to a post office that gets routed to another post office. So it hits that destination post office for that zip code. Now, once it has arrived, that post office is handling it and now looking at the next piece. It's looking at that street level, that NE street. All right, make sure it gets onto the right truck that's going to deliver those. Then it goes to 123, so it knows the right house. Okay, now it's addressed to Chad Green, going to the house number 123. But the mail stops at the door because the mail person does not bring the mail into the house and deliver it to the person specifically. It brings it to a border. And that mailbox, right, that's acting as that border, and then somebody's going to bring that mail into the house and then spread that out to maybe Chad's wife, daughter, whatever. And as appropriate, right? So that's where that kind of a boundary, when we talk about routing, Because what if Chad is, hollering for his wife in the other room? Well, there's no sense for that information to go outside the door and get routed back in. It stays inside the house. So it stays inside that network, that local area network. So now let's look at an actual addressing. When we talk about IPv4, we're going to stay with the version 4 for now. And we're going to understand how that actual address occurs. So I want to take a quick example of 192.168.0.10.10. Notice that there's the little dots. So what we have are 4 octets. And the reason they're called octets is because of the way they're represented. And each of those octets have a range of numbers from decimal numbers from 0 to 255. And I love that. The query is coming from inside the house. That's awesome. With IP, right, being the internet protocol, it's talking about how to reach an actual address. And each of the numbers, like I said, goes from 0 to 255. Now, that's friendly numbers for us. The computer doesn't care. That's what it handles everything in binary. So we need to take a look at that just briefly. So when we look at the IP version 4, we're looking at that address. We're going to split that up to actual binary information. First thing we notice is that it's 32 bits. With version 6, there's 64 bits. So it's twice as many bits, but it is a huge number of opportunities and addresses. So we should not actually run out of IPv6 for centuries. Whereas with IPv4, we already are running out with public addresses. Now, notice I say public. I'm going to show you the difference between private and public in just a moment. But first, when we look at a destination address of something like 192.168.0.10, how does it know? How does the router know if it's to go outside or stay inside to the with the local area network? And what's used is what's called a subnet mask. So when we look at how a subnet mask is applied, it's looking at the number of ones applied to each of the octets in binary. And it basically is looking from left to right, where's the one that changes to a 0. So in this case, it's 255, 255, 255.0. What this is saying is that the numbers on the left that are included with the ones is what's called a network address versus a host address. And what I'm also saying here is that I can have, remember that goes the numbers from 0 to 256, I can have 256. It's not truly the case, but I'll explain why in just a moment. 256 hosts for each of the networks of the network address. So what this is also saying is that 192.168.0 is the network, where 10 is a host number. And if I was to move one of the ones to a 0, and we move that line, that division over, then I'm also saying that now the number of hosts has decreased, while the number of networks has decreased. The number of hosts per network has increased. Now, we're looking at this numbers that range, in this case, for this example, 192.168.0. Well, there are classes of these addresses. So this is where we're going to begin, is when we look at the classes from A, B, and C. Now, technically, there are 5. Generally, you're not going to ever worry about D and E. So everything else is dealt with the A, B, C classes. So 0, quad 0, up through 127, 255, 255, 255 is a class A range. The class B is 128 up through just shy of 192. And then class C is 192 and up through 223.255, 255, 255. So notice what we're saying is that with class A, we have a less number of networks, 128, but 16.7 million addresses available. If we go to a class B, 16,384 networks, were just over 1 million available addresses. Class C, so with my example, that 192.168.0.10, that was a Class C address. So this is talking about classes. In just a moment, we're going to switch over to another type of describing networks, and it's called CIDR, which is classless interdomain routing. So when we talk about classes, understand that it's talking about a specific range. Now, if the 192.168.0 address, yes, I believe that is true, is the number of available addresses per network. I'm 90% sure on that. So if we look at an RFC 1918, which is request for comment 1918, and what they say is that there is a grouping of addresses inside those classes that are considered non-routable. So the routers really don't care, except that they've been programmed to not route destination addresses that are in these ranges. So anything in the 10 range is going to be a private network, a private address. 172.16 and up is going to be a private address. And then the 192.168/16, those are going to be private as well. So when I mentioned that 192.168.0.10 as a destination address, that is a private network address. So the router sees a destination of that and says, that's on the list, I'm not going to route that out to the internet. Which also means you cannot have a public IP address that's in this range and expect to get any traffic on that. It will not happen. So if you have a traffic going to that destination address, then it's coming back and going to stay inside the network, inside that LAN. Okay. When we talk about the size of our network, that LAN network, but also public, because when we get into understanding how big of a network should we have, we need to understand like how many devices we're going to use. Now, I'm going to slowly switch gears from the perspective of having home devices to cloud. And then we'll touch on a little bit as to why what I'm specifically doing this. So when we look at sizing a network, we need to understand how big of a network do we need, and how many IP addresses do we need to fulfill all of our needs, our requests there. So if we have, say, the number of devices in your house, and then you were to double it, for example, you still don't need a really big network. However, when you get into cloud networking, you still have IP version 4. You still have a network, but they're also going to have subnets. So let's look at a quick example. If I have a 10 network, and I'm using that /24, and I'll describe a little bit more about the CIDR in just a moment. But if I say I have a /24, what I'm really saying is that I want 256 addresses. So my range on that fourth octet is from 0 to 255. So I have 256 possible options. And this comes back with, and this is where I'm really getting into CIDR here, is that remember the subnet masking being applied. This is where we're able to see the number of bits being on and the number of bits being 0 on the right. So now what we're also saying is that I have a virtual network, maybe a virtual network if it's in the cloud, a 10 network /24, but I have a subnet that fulfills the entire range. What I could also do is change that size, right? If I did a /23, well, now moving 1 bit over, I'm doubling my size. So I went from 256 to 512. Now notice the third and fourth octet. So now I'm going from a 0.0 to a 1.255. So now I've got 256 twice. But what I could also do is split that up so that my network is still /23, but I have now two subnets that are taking up that 512, 256 each. And again, I can maybe just have a /24 network. So I got 256 available addresses, but I have subnets to break that up, maybe 128 apiece. Notice that my CIDR address, that 24 going to 25 there, is a binary, basically shifting the bit over. So what if I have a /23? So now I got 512 available addresses, but I now have 6 subnets. I'm pointing out here is that the subnets themselves do not have to be the same size as a neighboring subnet. They don't all have to be a 128, something like that. Now, you're not going to have a 60 available type thing. It's either going to be, so it will always be a factor of 2, right? So 512, 256, 128, 64, maybe even to a 32 size range. So why would I even do this? Why would I take a network and split them up into multiple subnets? The main reason we do that is so that we have a purpose for the subnet. So when I have my devices, and again, I need to understand how many devices do I think I'm going to have in each of the subnets. And you do have to kind of forecast a little bit and think ahead, especially in the cloud, because it's harder to fix things if you undersize something. So if I look at these 4 subnet addresses, something I can do is give it a purpose, such as maybe I have DMZ based um, uh, public facing traffic type of devices, maybe something like an Azure load balancer, or maybe I've got a public IP. Well, in this case, these are private addresses. But maybe a web server that's going to handle public facing traffic, or something to that effect, right? But maybe I've got a web servers that are also behind a firewall that is in the other subnet. Maybe I've got app servers running Linux or something else, that not necessarily websites per se. Maybe they're sent into a different subnet. My databases could be in a whole different subnet. Why would I do that? We're going to discuss it in more detail in just a moment, basically for security reasons, because I can apply security rules and apply them to the entire subnet and control traffic in or out of those subnets. So security is definitely a big thing. So when you are designing your network, you absolutely want to consider security as we do this. CIDR, when I was talking about that /24 representing 256 addresses, then there's 25. Obviously, you can go all the way up to /0, which means everything. But you can also bring it as far down as a /29, which only provides 8 available IP addresses. You can do this, but you cannot do a /30 in the cloud networks. And the reason why is both Azure and AWS. I'm not 100% about GCP. I'm probably so, but I can vouch for Azure and AWS. When you create a subnet, because this applies per subnet, there are 5 IP addresses that it reserves. So you cannot use them. Well, if you have a /30, you only have 4 IP addresses available. You don't even meet the minimum for 5, let alone more than that, so that you have available for your devices. So a /30 is not even possible. Well, it's not possible in the clouds. And then a 31 is not possible, because even if it's not a cloud, you still have, if you're like your home router, something like that, you still have 2 base address or base IP input addresses that you cannot use. They are reserved. So what are they reserved for? If we take the first 4, and we'll stay in the cloud in this reference, if we take the first 4 IP addresses of a subnet, they don't have to start at .0, but let's just take this example. .0 is your network address, called the network address. The .1 is your gateway address. .2 and .3 are used for DNS, and then .255, the end of that subnet address or address octet, is used what's called the broadcast address. So there are 5 in the cloud. There's 5 taken up and reserved anyway. So if you were to grab a subnet and you have your first, and you put a virtual machine on there, the first available address is going to be that .4. That's why, because 0, 1, 2, and 3 have already been reserved, and 255 is reserved. And if you have a CIDR of /32, you're not really going to do this when you're sizing a network or even your subnets, but you will see this, for example, in AWS and the security groups. When you apply a security group rule, and maybe you want to allow your home address, which would be public-facing address, and you want to add that to the rule that says, I am allowed from this home address to reach in maybe to a virtual machine or something like that, but basically onto your VPC, a virtual private cloud. You will see your address and then /32. You don't have to do a /32, but that's generally what you see, meaning that this IP address and this IP address alone. Okay, now we're going to shift gears one more time. And we're going to look at when we have traffic coming from a laptop going out to the internet, because I want to go to maybe usergroup.tv. We have a thing called network address translation that's going on. So with my laptop, let's say that I've got an internal address given to me by what's called the DHCP, the Dynamic Host Configuration Protocol, which is usually done by a router. And so when I got onto the network, it gave me that IP address that is not being used by another device. So my computer has 192.168.0.5, and I want to get out to some web server. Well, my home address, because all of these devices go right to a router, and there's only one public, at least at my house. Now, obviously, this is not for everybody. You might have a business line, which you can get multiple public-facing IP addresses, and that's okay. What I'm going to do is, just for my analogies, talk about one public IP address. And I'm just picking out an idea of 40.134.210.98. So as I'm going to this web server, and if you want to know what your public IP address is, you can go right now to whatismyipaddress.com, and it will tell you what your address is, because that information is in every packet of data going out. Because when we're going out to that website, that packet of that request going to the web server is getting through the router, and the server that is taking that public traffic knows that your address is 40.134.210.98. It cannot be 192.168.0.5 because that's internal only, and that's not a routable address. So what if we have multiple devices on that network, which most of us do anyway? Well, it's still the same public IP address. So what happens then is, as this information is going out and getting out to a web server, the router is keeping track of who is making the request, basically which device is making a request. And every device opens a port for handling the communication, the request and the response. So in this case, we're going to talk about port address translation, because with network address translation, the web servers on the outside, doesn't have to be a web server, but you get my point, on the outside know that it's your one public home address where the response of that request is going to come to. So with port address translation, it goes along with network address translation. However, there's ports involved. So with every IP address, there are 65,536 available ports. And we'll talk about more details on some of those that you may already recognize in just a moment. But as I'm coming out, let's say from the one laptop, 192.168.0.5, I'm going out to Google, and well, it sees that an outbound port of 45123 has been opened from the network, from the router, and is going out to the web server. The response comes back to that IP address, that 40.134.210.98 address at that port. So the request is coming back to that port. The router finds it on its table that it is managing and routes that response back to the requesting device, be it that laptop versus the other one. Because maybe while that other device is on the network, it's having its own communication going on, and its responses are coming back to a different port that was opened for it. Now, if I've got all these devices and I have one public IP address on this router, and I only have, I say only have 65,536 ports, isn't it possible that I could have what's called port exhaustion? You can, especially if you're doing stuff in the cloud, because you could have a ton of outbound conversations going on, and you may have to have multiple IP addresses, and there's ways to do this, certainly with Azure load balancers and with the NAT gateways that AWS has. So there, the 65,536, which is 16 bits, the 0 port through 1023 are reserved. So you notice that the ports that the router opened are really high numbers. You're going to find that the really high number of ports are for those outbound conversations. When a conversation is going on, let's say I went to google.com, the response came back, the port is held open for a while until it's been idle for a minimum amount of time. And that's, I don't remember exactly what that setting is, but I think you can change that. After that time has elapsed, that idle time, then the router will close that port. And it also means it's available for another piece of traffic. Now, here's the thing. If the request from the laptop on the left is separate from the request from the laptop on the right, what if I have multiple tabs open on one of the laptops? Every tab could have one or more ports open, because a tab viewing a web page for however you're going to make this request could have one or more outbound requests going out. So you could have multiple ports open just for one tab. This is also why you can have, I hope you never have port exhaustion, but if you've got that many laptops, maybe you've got a lot of kids in the house and you got all these devices, and they're open up a ton of ports, or a ton of ports for that conversations. It is possible that you could hit port exhaustion. Not likely, but it's very possible. I just want to make sure you're aware of it. So I mentioned that we see several of those ports reserved. Here's a couple of the common ports that you may see. 20 and 21 for the data and command for FTP. 22 for SSH, that's secure shell. 25 for SMTP, secure simple mail transfer protocol. 53 for DNS, which is that domain name service. 80 and 443. So we're a lot of times you're going to see where there's actually other type of communication going on, where if something's coming in on port 80, say for a website, it's going to get redirected to a different port. You can do it and set it up depending on how you're going to do this, but you can set it up to go to a different IP address based on ports. But you generally, what you see, at least with 80 and 443, is that your web traffic goes to 443. And hopefully there is what's called TLS, transport layer security, because there is SSL, but it's more deprecated in favor of TLS, which SSL secure circuit, what is it? secure socket layer. And this is where you're going to see a lot of those HTTPS type things on, let's say, Twitch, for example. And port 1443 for SQL Server. And there's obviously many others out there for like RabbitMQ, for Mongo, for Postgres, things like that. Now, there's also a thing called the OSI model. And I'm going to explain this really quickly, but also to explain why this, at least the OSI model, matters in just a second. So we have the OSI models, Open System Interconnect model, and you have physical layers. So this is going to be that copper or fiber. Maybe in a data center, it's the actual physical lines going from one router or a switch to another. But the data that is on there starting to get translated on layer 2. Then it needs to hit a destination of, say, an IP address. Well, that IP, the Internet Protocol, is dealt with on layer 3. Then it looks at what kind of conversation are we having? Is it TCP or is it UDP? TCP is Transport Control Protocol, and UDP is User Datagram Protocol. So when I mentioned DNS earlier, UDP is done with DNS. Whereas not with TCP, but if you do something like a web server, that's done with TCP-based conversations. Then session and then presentation. A lot of your secure handling of that traffic is dealt with at layer 6. And then layer 7 is that application layer. If you've done any kind of like MVC programming, and do you remember the R for routing? I know they leave the letter off, but you would, when a request is coming in, it gets routed to the controller that is handling that request. Well, that routing that for MVC, for example, is done at layer 7. It's an application that's doing that, the code level, if you will. I say that, but obviously there's code at different layers, depending on the other stuff that you have going on. Okay, so why does all of this matter? Why does not just the open system interconnect model matter, but why are we talking about networking? Why do I think programmers ought to know about networking? Well, if we look at the OSI model, and you notice that layer 4 and layer 7 are called out differently. More and more developers are doing things in the cloud. And so we need to understand how and when a lot of the infrastructure is used for things like an Azure load balancer and an AWS network load balancer. They handle traffic at layer 4. So when we're designing our infrastructure for handling our websites, for our businesses, things like that, it is better for us to know about this information. Now, for me, I was one of those that was a programmer, but also responsible for building up the infrastructure for doing this. Layer 7 is done with Azure App Gateway and AWS Application Load Balancer, or if you have something like Nginx, I don't think it's free, but the Nginx Load Balancer handles things at layer 7. So this is what I'm touching on. Why do programmers need to know about this stuff? Well, for one thing, security. Security is getting more and more of a frontline topic for us developers. And hence why we have what's called shift left. The emphasis on when to begin the dealing with the security needs is shifting left in the process of the SDLC, that software development lifecycle. So now it's becoming more and more in our face as for us to be dealing with at design, not just at coding, not just at testing, not just at deployment, not just at runtime, but even so far back as we're designing our products, our code, our infrastructure, everything like that. So that emphasis is shifting left, which means there's more emphasis on us to understand how to handle security needs. And as well as splitting up resource needs, maybe like understanding how load balancers work and understanding the architecture. Maybe you're not the designer of it, But I'm a cloud architect, and if I'm working with developers and they understand more about the architecture that's hosting their applications that they are developing, then they have a better sense of how to handle things, maybe secure, both high availability, disaster recovery, how messaging is needed at various times, when and why you shouldn't do microservices, that kind of thing. And as well, obviously, one of the side effects is you get a higher career growth, right? The more you know, the more that you're going to able to provide to your employer, to clients, etc. So speaking of security, and we're talking about those subnets earlier, well, this is what's called a north, south, east, west security model, where I have got the internet coming with somebody who's making a request into my application that's hosted inside a cloud. And maybe I've got several virtual machines set up. Maybe there are other cloud native solutions, but we'll stick with this for right now just so I can get the concept conveyed. The request is coming in from the top, and it's coming into, maybe it's a virtual machine handling things at the DMZ level. It's public facing. And I need the request to be handled there. And then it's going to be, depending on the type of request, maybe it's sent over to a web server, maybe it's an application server. And then they make a request, that code in there makes a request to the database to get some of that information. So in that respect, that's north-south. Now, when I have multiple servers at those different layers, such as DMZ or app server type layers, there may be times when servers are expected to talk with each other, or maybe for only very tight reasons, such as keeping a pulse check for health checks and for high availability. But it may also be where a scenario that if there's code running on one server and it has absolutely no business reason to ever contact another server, certainly on the same level, the same subnet as itself, then you can put in rules to prevent that. Now, it's one of those things where, why would I do that even on a private network? The idea here is the what if. What if in your code base, you grabbed your cousin's college roommate's brother's NuGet package or NPM package or something like that. You brought that into your code base and it's doing its job, but what you don't know is that it's also sniffing the network and trying to send data out. That's why you want to make sure that you're controlling that network traffic, even to other servers that are just like it. If there's not a business reason for them to communicate, make sure it doesn't happen. Provide that east-west security as well. Okay. Switching gears. Now, let's talk about Azure Virtual Networks. And so we've picked out a virtual network where we sized it to what we need, and we've got two different subnets. Now, with subnets, you can assign them to route tables, and a route table is a list of rules that says what controlling the network traffic. For example, in the first subnet, I'm associating it to a route table called A, and it has some rules that it's allowed to talk to anything on 192.168.0.0/24, but it also has another rule that says quad zeros /0 says if you're going anywhere else, internet, whatever, if you're going anywhere else, forward the traffic to the firewall. That way, you can use firewall rules to see if it's really allowed outbound. Because what if that package that you brought in has sniffed the network, and in my microservices talk, I give a scenario where what if that microservice is processing your paycheck? And you didn't secure it, you didn't control who can call it. Now some data has gotten a hold of your paycheck information and is now sending data outside of that network, maybe to some other place in the world that it doesn't ever belong. You can set what's called the next hop and control that traffic destined for that area to something like a firewall. Now, in the second subnet, For this example, I have it associated with route table B, and it does not have a quad 0 rule. So basically, it's not allowing anything out. All right, so double checking my notes right quick. Now, with AWS and VPC, that virtual private cloud, it does the same thing. So with that association, instead of quad zeros for the rule, what you see in that route table is what's called an IGW, an internet gateway. And if it has that internet gateway, it's considered a public subnet. If there is no rule for that, it's called a private subnet. Okay, I already talked on that. Load balancers. I'm going to talk on this very briefly. So load balancers help separate the load coming in. This helps to spread that load across multiple containers, maybe multiple pods in a Kubernetes. So you have a Kubernetes service. That's essentially what that is, a load balancer. And if you do AKS and you set up a service, it built an Azure load balancer to handle that, which also means, because it's an Azure load balancer, you know that that data, that traffic is handled at layer 4. So it's only dealing with the TCP level, TCP and IP in that combination. So depending on what needs we have, we may look to see if we need to do a layer 4 Azure load balancer or a AWS network load balancer. If we have a different type of need, what we may use is a layer 7. So in that case, we'll set up an Azure App Gateway or an AWS application load balancer. So inside the two, regarding security groups, they both have security groups, and those security groups are stateful versus with the NACLs in AWS, they're called stateless. Now, here's the biggest difference on that. With when you have that conversation going out to a destination, it's going past a router, maybe it's going, in this case, it's going past a security group, it goes through a rule, and that rule allows it to go out. Well, the response needs to come back in. When the security group says, well, this is a response to the request that just came through there, and it's held that open, then that's stateful, meaning that it's going to keep the state of that, essentially that it's not a port, but it's the rule as it's applied, allows the response to come back. With a NACL, it is stateless, meaning you have outbound or you have inbound, you have to apply rules for the opposite directions. So got to be kind of careful how you set that up. But I was going to say that with AWS and your VPCs, you're more likely to be using security groups for handling that kind of thing. Rarely will you use NACLs. Now, not never, but more likely you're going to be using security groups. So with that, I am at the end and available for any questions. I've been trying to keep an eye on Twitch as far as the chat, and I didn't see too many questions, but if you have any questions, now's a good time to bring those up. And so myself, Sean Whitesell, Code with Sean on Twitch, Senior Cloud Architect with ArchitectNow, Microsoft MVP. I run the .NET user group here in Tulsa. Frequent conference speaker. That's how I met Michael Richardson, and great guy. I really appreciate the discussions I have with him. Just a fantastic guy. There is my website, SeanWhitesell.com. However, I rarely use that. Like I said, I do need to get back on to Twitch and stream, but that'll be sometime later. So we'll see. I don't know yet. Other than that, Michael, take it away.
Thank you, Sean. Thank you for helping us learn a little bit about network architecture. That was super interesting. I really appreciate all that you taught us today. Give me a little applause in the chat for Sean, please. Sean, thank you very much. We'll see you in the Zoom chat after this. So,
yep.
I'll